The various thermodynamic potentials that we had introduced are additive in the following sense. If you have a composite system composed of two parts, A and B, and both parts are coupled to the same reservoir. So we have a reservoir here, and it's coupled to both parts of your system. I don't need to specify here what kind of reservoir that is. That could be a heat bath, which maintains a constant temperature, or a volume reservoir that maintains a constant pressure, any kind of reservoir. And depending on the type of reservoir, equilibrium of the two systems is characterized by a certain choice of thermodynamic potential. Now, regarding that suitable potential, the thermodynamic potential for the entire system, for the composite system of A and B together, is just the sum of the thermodynamic potentials of A and B separately. So in words, when we have a composite system and all parts, maybe even more than two, all parts are coupled to the same reservoir, or reservoirs, if you control, say, temperature and pressure, then the corresponding thermodynamic potential is additive. Let's consider an example. Let's consider two systems, A and B, coupled to a thermostat. This implies that the appropriate potential, and they are enclosed inside a fixed volume, this entails that the appropriate potential is the free energy F. Now let's look at the free energy of the composite system. The free energy of the composite system, by definition, equals the internal energy of the composite system minus T times entropy, temperature times entropy. Since both parts of the system are coupled to the same reservoir with fixed temperature T of the reservoir, the composite system also, as a whole, is also coupled to this reservoir with temperature T of the reservoir times entropy of the composite system. Now the internal energy is additive when you put two systems together. So this is UA plus UB, and so is the entropy. The entropy of the composite system is the sum of the individual entropies. So we can write this as UA minus temperature of the reservoir times SA plus UB minus temperature of the reservoir times entropy of B. And you immediately recognize that this is the free energy of subsystem A, and that is the free energy of subsystem B. So indeed, the free energy of the entire system is the sum of the free energies of the subsystems. This only works because both subsystems are coupled to the same reservoir. This no longer holds if A and B are coupled to different reservoirs. So maybe heat baths with different temperatures, or one coupled to a temperature reservoir and the other one to a heat reservoir, and the other coupled to a volume reservoir. Yeah? So this is an important assumption, that they are coupled to the same reservoir. Up to this point, we did not assume that a given system is in equilibrium. We defined the various potentials for arbitrary states of the system. Only the reservoirs were assumed to be in equilibrium. But the system itself, the system of interest itself, could be in an arbitrary state. That's why we wrote F of rho, for example, or G of rho. So we could assign a potential to an arbitrary state of the system. Only now, let's look at the equilibrium case. In equilibrium, not only the reservoirs have well-defined temperatures, pressures, chemical potentials, and so on, but also the system itself. So when the system is in equilibrium with the reservoir, then the system, first of all, has a well-defined temperature, and this temperature is the same as the temperature of the reservoir. So we no longer have to write explicitly that temperature, pressure, and chemical potential refer to the reservoir. We can instead simply write T, P, and mu. When we do that, then we imply that not only the reservoir but also the system itself have well-defined values for these intensive variables. Secondly, in our definitions of the potentials, featured the entropy of the state rho, the internal energy, meaning the energy expectation value in a certain state rho, and so on. That's because we defined the various potentials for arbitrary states. When we are in equilibrium, then we can replace the rho by an equilibrium state. So we can write this as entropy of the equilibrium state, internal energy of the equilibrium state, and so on. But these, in line with our notation in thermodynamics, we simply denote by S, U, and so on. So we simply omit the explicit dependence on a state rho. When we write S, U, and so on without explicit dependence on rho, then we mean the equilibrium values. And finally, for the potential itself, say the free energy, we have so far written free energy as a function of the temperature of the reservoir, the volume, and the state of the system. Then we said the temperature of the reservoir is now also the temperature of the state, and we simply denote it by T. Volume is the volume, and the density matrix is the equilibrium state, but this we write simply as F, or as a function of temperature and volume, and again we omit the explicit dependence on the state, and when we do that we mean that we are in equilibrium. We can once again draw our Guggenheim square. Good physicists have studied under very fine teachers. And now also in this Guggenheim square, I no longer write the dependence on rho of the potentials and of the entropy, and I omit the subscript reservoir of the pressure and temperature. And now in the equilibrium case, it is once again true, as in the earlier Guggenheim squares that we had encountered, that you can obtain the conjugate of a thermodynamic variable, so of one of the sides of the square, by taking the partial derivatives. So we have again this pattern that a corner of the Guggenheim square is a potential. The adjacent sides, so in this case pressure and entropy, are the natural variables of that potential. So this potential, in this case the enthalpy, is a function of the adjacent sides, which are its natural variables. And now the conjugate of pressure, for example the volume, that would be the volume. So on the opposite side, you have the conjugate of a natural variable. And here now it is true in equilibrium. Earlier outside of equilibrium this was not true, but in equilibrium it is again true that you can obtain the conjugate of a thermodynamic variable by taking the partial derivative of a potential. For example, here you can say that the volume is the partial derivative of the enthalpy with respect to pressure, keeping the other natural variable of the enthalpy constant, keeping that fixed, namely the entropy. And there's a positive sign because the natural variable pressure with respect to which I take the partial derivative is at the top of the arrow, and therefore there's a plus sign, whereas another example, take the partial derivative of the free energy with respect to its natural variable temperature at fixed volume. Here the temperature is at the end, at the tail of an arrow, and therefore we get a minus sign, and we obtain the entropy, which is the conjugate of temperature with respect to free energy. Yeah, so all these nice relationships that you had seen in earlier Guggenheim squares now once again work. Some of the thermodynamic potentials are related to partition functions. For example, the free energy as a function of temperature and volume equals minus kT times the log of the canonical partition function. You can see that by considering the entropy. We know from our general framework that the entropy in the canonical ensemble, the entropy is given by Boltzmann's constant times log of the canonical partition function plus beta times internal energy. When you multiply this with temperature, then you find that temperature times entropy equals kT log of the canonical partition function. I forgot a Boltzmann constant here. When I multiply this by T, then I have kT times beta, this is 1, so I have plus internal energy, and now you see immediately when you move the Ts on the right hand side, then you have on the right hand side you have U minus Ts, and you move the kT log partition function on the left hand side, which is, so you have free energy is minus kT log of the canonical partition function. In a similar fashion, you can show that the grand potential, which is a function of temperature, chemical potential and volume, is related to the grand canonical partition function by a factor minus kT. It's minus kT times the log of the grand canonical partition function, which is a function of temperature, chemical potential and volume. Now this comes in very handy because what you need in practice is often one of the thermodynamic potentials. You perform an experiment under certain experimental conditions, coupled to certain reservoirs or subject to certain barriers and constraints. Depending on that setup, you need a certain thermodynamic potential. Coming from statistical mechanics, what you can calculate microscopically is a partition function. So when you come from a microscopic model, you obtain a partition function. Somehow you would like to connect the two. Yeah? What you need to describe an experiment is a thermodynamic potential. What you calculate statistically is a partition function. And these relations provide the link between the two. Now, it may be that free energy and grand potential are not the potential that you need. You might need, say, the enthalpy or the free enthalpy for a certain experiment. So you still need a procedure to go from one of these two potentials to the potential that you need. And this is once again a Legendre transform that you had already encountered earlier in a different context, and which I'm going to show next in a specific example. But let me note on this page just the general idea for a typical procedure. What you do is you have a microscopic model, then you calculate a partition function based on this model, then you determine free energy or grand potential. Then you do a Legendre transform, which we are going to discuss next, to obtain the potential needed to describe a certain experiment, which might also be the free enthalpy or the enthalpy, depending on the setup. So what is the Legendre transformation? Let me just remind you of the basic idea and then show it to you in a specific example. The starting point of the Legendre transformation is one of the potentials, which was either given to you by someone else or which you obtained, say, by calculating the log of a partition function. So you obtain that from a microscopic model. But if this is not the potential that you need, you can move from this potential to another potential. You move along the sides of the Guggenheim square until you reach the potential that you need by the following two steps. You move along one of the arrows in this Guggenheim square, and when you do that, depending on whether you go parallel or anti-parallel to this arrow, you add or subtract the product of the two ends of the arrow. So thereby adding or subtracting the product of the two opposite ends, so these are pairs of thermodynamic variables. And then you have to change variables because each potential has its own natural variables. So you want the new potential to be expressed as a function of its proper natural variables. So you have to effect a change of variables in order to get the correct dependence of the new potential on its natural variables. To make this more concrete, let's look at a specific example. Let's look at a classical perfect gas. And what we learned and what we calculated earlier in the course is starting from a microscopic model was the log of the grand canonical partition function, which is a function of the Lagrange parameters beta and alpha and of the volume. And we found that this was up to a constant of proportionality. This was given by e to the alpha times volume times beta inverse temperature to the power minus 3/2. So this is the dependence, the form of the dependence on the natural variables of the grand canonical partition function. We had also learned that the log of the grand canonical partition function equals the particle number. This is what we already know from our treatment of the classical perfect gas in statistical mechanics. Now let's suppose that we perform an experiment in open air with a classical perfect gas. In open air means the gas is coupled to the atmosphere. It happens in the atmosphere. The atmosphere acts as a reservoir, a heat and volume reservoir, maintaining a constant temperature and pressure. The appropriate thermodynamic potential for that is the free enthalpy. So the objective now is to start from this grand canonical partition function which we had calculated and obtain from this the free enthalpy of the classical perfect gas. As a first step, let me draw one conclusion from this result, from this earlier result. We can, in the first equation, we can replace on the left-hand side, we can replace the log of the grand canonical partition function by n, by the total particle number. And we can solve the equation for alpha. And then we find that alpha equals the log of particle density plus 3/2 the log of beta plus some constant. Conclusion number 1. Next, what I would like to do, the plan is the following. First, I would like to relate the grand canonical partition function to the canonical partition function. Then the canonical partition function to the free energy. And then by a Legendre transformation, go from the free energy to the free enthalpy. This is the plan. Maybe let's sketch it here on the side. This is my overall plan. I go from the log of the grand canonical partition function to the log of the canonical partition function, from this to the free energy, and from that to the free enthalpy. And the last step the first step is already a Legendre transform of the type that we had encountered earlier. And the last step is also a Legendre transform. But they play in two different Guggenheim squares. The first step from the grand canonical to the canonical partition function is a step that we had already discussed earlier in the course. Remember that the logs of the two partition functions are related by our general framework. They are related by this equation. The log of the canonical partition function equals the log of the grand canonical partition function minus alpha times particle number. This you can read from a different Guggenheim square. Let me show it to you. We had this in the chapter on the thermodynamic limit when we talked about the equivalence of ensembles. We had a Guggenheim square in which the log of the grand canonical partition function and the log of the canonical partition function featured. And with our usual tricks, we can read from this Guggenheim square that the log of the canonical is the log of the grand canonical partition function minus alpha times n. This is what we are using here. The log of the grand canonical partition function is equal to the particle number. So in fact, this is nothing but 1 minus alpha times the particle number. For alpha, we use the result in the previous line. And then we obtain n times the log of the volume plus 3/2 n times the log of temperature plus terms that only depend on particle number, but not on T and V. And it will, for our purposes, it will be good enough to write it in this form. By the equation on the previous page, we know that the free energy as a function of temperature and volume is given by minus kT times the log of the canonical partition function. We use the results that we had just obtained for the canonical partition function. Then this equals minus nkt log of the volume minus 3/2 nkt log of temperature minus kt times a function that depends on particle number only. And since we are interested in situations in which the particle number is fixed, we can treat this function of n like a constant, because the particle number in the experiment that we are considering, the particle number is not changing, the particle number is fixed, so this function of n is just like a constant. What do we have to do? Now we have the free energy. Free energy as a function of temperature and volume. In our final step, we want to move from the free energy to the free enthalpy. And let's recall once again the Guggenheim square. Good physicists have studied under very fine teachers. So this is the Guggenheim square. So what do we have to do? To go from the free energy to the free enthalpy, we move parallel to this vertical arrow. This vertical arrow has at its ends pressure and volume. And we move parallel to that arrow, we move upwards. So we have to add to the free energy, we have to add pressure times volume. This is one aspect. The other aspect is that free energy has as its natural variables temperature and volume, whereas free enthalpy has as its natural variables temperature and pressure, so we have to change variables. So we need to find the function free enthalpy, G, as a function of temperature and pressure. We learned that we know that this is free energy, which is a function of temperature and volume, plus pressure times volume. But now we want to get rid of the volume and instead have a dependency on pressure. So what we need to do is we have to express volume in turn as a function of temperature and pressure, both here and there. How can we do that? We also learn from the Guggenheim square that the partial derivative of the free energy with respect to volume at fixed temperature, that this equals minus the pressure. What is the partial derivative of free energy with respect to volume? How does the free energy depend on volume? It's minus nkt times the log of the volume, and all the other terms are independent of volume. When I take the partial with respect to volume, then the partial of the log gives me a 1 over volume, so I get a minus nkt over volume. And I know that this must be minus the pressure. So, and of course this is nothing but the ideal gas equation. And we just re-derived the ideal gas equation, and we can solve that for the volume, and we obtain the volume as a function of temperature and pressure. This is nkt over pressure. I don't write explicitly the dependence on n because throughout we are assuming that the particle number n is fixed. So I don't carry with me the explicit dependence on n because it's fixed anyway. Now we have volume as a function of temperature and pressure, and this function we insert here. And when we do that, then we obtain the free enthalpy. The result is that the free enthalpy as a function of temperature and pressure is equal to nkt times the log of pressure over temperature to the power 5/2 minus kt times some function which is different from the function above, some function which depends only on particle number. We can now use the formula that we found for the free enthalpy of a classical perfect gas to verify, to check some of the relations, thermodynamic relations that we know for a classical perfect gas. For example, again, the Guggenheim square, which I show in gray, tells us that the partial derivative of the free enthalpy with respect to pressure should yield the volume. So we should be able to calculate, when we are given the free enthalpy, we should be able to calculate the volume by taking the partial derivative of the free enthalpy with respect to pressure at fixed temperature. Now this is pretty easy because the only way that G depends on pressure is this logarithm. Derivative of the log is 1 over pressure, and we obtain nkt over pressure, which is once again the ideal gas equation. So many ways leads to the ideal gas equation. Here's another one. Another quantity that we could calculate, we could look at the entropy. According to the Guggenheim square, the entropy is the conjugate of temperature, so we should obtain that by taking the partial of the free enthalpy with respect to temperature at fixed pressure, and since temperatures at the tail of the arrow is a minus sign, so we look at the dependency of G on temperature and take the derivative, and this gives nk times the log of temperature to the power 5/2 over pressure plus a constant where the constant may depend on particle number, but since we keep that fixed throughout, we can consider that as a constant. So strictly speaking, it depends on n, but none of the other thermodynamic variables. And from this, for example, we can conclude that in a quasi-static adiabatic process, adiabatic means no heat exchange, quasi-static means very slow, sufficiently slow so that work is reversible. So when we perform reversible work on a system, then it's quasi-static and there's no heat exchange, and then the entropy is conserved. The entropy is constant. Now we learn from this result on the previous line that constant entropy for a classical perfect gas means that temperature to the power 5/2 over pressure that this is constant. So in a quasi-static adiabatic process, we know that the pressure is proportional to the temperature to the power 5/2. And this is only one out of many conclusions that you can draw from these various potentials. The thermodynamic potentials also appear when we, or turn out to be useful when we consider exchanges, energy exchanges between two systems, A and B, in the presence of reservoirs. And we consider the general setting shown above, that we have two systems A and B, and A can exchange energy with B, and A is also possibly coupled to a reservoir. And there are different cases depending on the type of reservoir that system A is coupled to. About system B, we don't make any assumptions whether it is coupled to a reservoir or not. It may or may not be coupled to a reservoir. It may be the same or a different reservoir. We don't care. All we know and we distinguish in the various cases is the type of reservoir that system A is coupled to. The first case, in a way a trivial case, is where A is not coupled to any reservoir at all. And when you think about the amount of energy transferred from A to B, then this simply equals the change or minus the change of internal energy of A. So the internal energy of A is reduced by d UA, and this, due to the first law, energy conservation, this is precisely equal to the energy that must flow from A to B. Energy can flow in various forms, and I distinguish it here by various symbols and colors. Energy can be transferred in the form of heat. Energy can be transferred in the form of mechanical work, and more specifically, what is called pressure volume work. So that is mechanical work due to, or mechanical work that involves a change in volume. So under some pressure, there's a change in volume, and this is a specific type of mechanical work called pressure volume work. That's the kind of mechanical work that we've always considered so far. But there may be other types of work as well, and these other types might be mechanical work or even non-mechanical forms of work. For example, it may be work, energy in the form of rotation. That's also called shaft work. When you have you drive a turbine, then you generate a rotation, and there's rotational energy, and you can transfer rotational energy from A to B. You can have electrical work or magnetic work. You can also have exchange of energy in the form of a particle exchange, but this is just one out of many possibilities. So, so the green symbol subsumes all so-called non-expansion work, so all work other than pressure volume work, all kinds of work that do not involve a change in volume. And you can have any of these types of, or any of these forms of work, and in the first case also of heat, being transferred from A to B. In the second case, system A is coupled to a heat bath. So you can have an exchange of heat between A and the heat bath. And between A and B, you allow all other forms of work. So you allow pressure volume work, and you allow other forms of work, so non-expansion work, but you do not allow exchange of heat. And the way I try to symbolize that is this shaded area, so that represents thermal insulation, no flow of heat. But this might be a movable piston, so that you can transfer pressure volume work, but you can also transfer any other kind of work, be it mechanical or non-mechanical. And then you wonder, what is the amount of energy transferred from A to B? This is, again, the change of internal, minus the change of internal energy of A, but corrected by the amount of heat received from the reservoir. So you have to consider, rather than dU, you have to consider dU minus the amount of heat received from the heat bath, from the reservoir, which is TdS. We are assuming throughout that these processes are quasi-static, so we can always consider A to be in equilibrium, and the reservoirs are in equilibrium anyway. So the amount of heat received from the reservoir is TdS of system A. And then it doesn't hurt to add another term, SdT, because the temperature T is kept fixed by the reservoir. Therefore, dt is 0. So we're just adding 0, and this doesn't change anything. But this allows us to use the product rule, TdS minus SdT. That's just the differential of Ts. And then you can combine it with the differential of internal energy, and you see this is just the differential of free energy. Yeah? So minus dF minus differential of free energy of system A, that's the amount of energy in the form of work, any kind of work, be it pressure volume or other forms of work, transferred from A to B, in the presence of a heat reservoir that communicates with A. In a third case, you have the subsystem A coupled to a volume reservoir, so it can exchange energy with the volume reservoir in the form of pressure volume work. There's a movable piston, and that maintains a constant pressure of system A, and work can be done by the reservoir on system A, and that's pressure volume work. There's no other coupling to the environment. That's why I drew this shaded area around this whole arrangement. So there's no exchange of heat with the reservoir or with the environment in general. And with system B, the system A can exchange then all other forms of energy, and that can be heat, and this can be non-expansion work, so all other forms of work. And there's a similar argument. The amount of energy transferred from A to B, that's minus the change of internal energy of A, but now corrected by the amount of pressure volume work received from the reservoir, from the volume reservoir, and that's minus PdV. You can do the same trick as in the second case. You add the VdP, which doesn't hurt because dP is 0, the pressure is kept constant. And then you can combine these terms into minus the change of enthalpy. And finally, case number 4, this is of particular interest when you have experiments in open air. So the reservoir is the atmosphere, maintains a constant temperature and pressure, exchanges with system A energy in the form of heat and pressure volume work, maintaining a constant pressure. And then the only form of energy that A can exchange with B is non-expansion work. So this could be once again, it could be electrical, magnetic, and so on, you name it. And you do the same trick and you find the energy flow is minus the change of free enthalpy. So to summarize these 2 pages, there are different scenarios. System A can be coupled to different kinds of reservoirs. In exchange with system B, then the remaining forms of energy. And when you want to know how much energy can be transferred to system B, then the answer is always a change of some thermodynamic potential depending on the kind of reservoir that it's coupled to. I would like to revisit the issue of the thermodynamic stability of a system. We had earlier discussed the thermodynamic stability of an isolated system, and remember that the criterion for stability was that the entropy reaches a genuine maximum when the system is homogeneous. And as soon as you introduce inhomogeneities in the system, then you move away from the maximum and the system tends to restore homogeneity. It goes back to the entropy maximum and thereby it restores homogeneity. And this presupposes that in the homogeneous state, the system attains a genuine maximum of entropy. We have in the meantime replaced the principle of maximum entropy by the principle of minimum energy. And this is where the thermodynamic potentials first appeared. We looked at situations where the system is coupled to different types of reservoirs, and in these cases, the equilibrium was distinguished by being that state where the appropriate thermodynamic potential reaches a minimum. And in order for this equilibrium to be stable, this must be a genuine minimum. So we have a new criterion for stability in the presence of a reservoir, namely that the homogeneous macrostate is a genuine minimum of the appropriate potential, depending on the type of reservoir that the system is coupled to. Consider the following example, an example that we had looked at before. We take a system coupled to a heat bath. Similar to what we had done before, let's say this is a gas. Now we split the gas in 2 halves. If the system is homogeneous, then in the left half we should have half the volume, half the particles, and the same temperature T. And in the right half we should have the other half of the volume, the other half of the particles, and again the same temperature. This is if the system is homogeneous. If the system were inhomogeneous, then it could be, one example, that we still have half the particles on the left, half the particles on the right, but we have in the left half we have a lower density than in the right half. So this half of the particles on the left is in a larger volume. So we have here half the volume plus some delta volume, and on the right we have correspondingly a smaller volume. Yeah, so we have two halves, one with a lower density than the other, particle density. So this is clearly an inhomogeneous state. Now, stability requires that the free energy of the homogeneous state is strictly smaller than the free energy of the inhomogeneous state. In the presence of a reservoir, we had learned that equilibrium is characterized by some appropriate thermodynamic potential reaching a minimum. And we must be sure, if we want to have stability, thermodynamic stability, we must be sure that the homogeneous phase, the homogeneous state, is the one that corresponds to equilibrium. So in this example that we are considering, we have a system coupled to a heat bath, maintained at a constant temperature, and then we split the system in two halves, and now we can distribute the extensive quantities either evenly or unevenly between the two halves. When we split them evenly, then we have a homogeneous state. If we split them unevenly, then we have an inhomogeneous state. So on the left-hand side, we have in the left half the volume, half the particles, and the same on the right. On the right-hand side, we split one of the two extensive variables, we split unevenly between the two halves. So we still have left and right half the particle number, but we divided the volume unevenly. And in doing so, we generated an inhomogeneous state. And we say that the system is thermodynamically stable if it's the homogeneous state that has the lowest thermodynamic potential and therefore corresponds to equilibrium. So if we have this strict inequality indicated here. So we applying the same argument as we had done before in the case of an isolated system, where we said equilibrium corresponds to a genuine maximum of the entropy, and that must be the homogeneous state. We apply the same type of argument, only that now instead of entropy, we are considering a potential. Instead of maximizing, we are now minimizing. And whereas originally for an isolated system and for the entropy, we found the condition that the entropy must be a strictly concave function because it must be a genuine maximum at the homogeneous state. We now must require that the potential is a convex function. This means mathematically that, say in this scenario that I just showed, where I distribute the volume unevenly, convexity means that the second order partial derivative of free energy with respect to volume at constant temperature, that this must be strictly positive. So here we have the second order partial derivative with respect to the extensive variable that we distribute unevenly. And it must be one of the natural variables of the appropriate potential. So with respect to an extensive natural variable. Knowing that the first order partial of the free energy with respect to volume, the first order partial derivative is minus the pressure. This convexity requirement is equivalent to the requirement that minus the partial derivative of pressure with respect to volume at fixed temperature must be strictly positive, and this is equivalent to the requirement that minus the partial of volume with respect to pressure at constant temperature is also strictly positive. We can multiply with 1 over volume, and then we identify that the left-hand side is nothing but the isothermal compressibility. So we find the stability condition, or we recover a stability condition that we had already derived earlier using the entropy argument. Namely that the isothermal compressibility of a stable substance must be strictly larger than 0, and it must be finite as well. And we found the stability condition in a very straightforward manner. The derivation was now much simpler than the derivation that we had looked at before.